Hello, everybody. My name is Andy Pye. I'm consulting editor at DFA Manufacturing Media, which publishes a range of publications in print and online around manufacturing and automation. A very warm welcome to this afternoon session of Talking Industry, sponsored by KUKA, and it's going to cover the advantages of robot welding in industrial applications. We have an expert panel of 5 speakers who will deliver their experience, opinions, and information on how robots are shaping the future of the welding industry, whilst we recognise that there is an increasing skills shortage problem and an absence of welders with competent skills to meet the demands of industry. So welcome to this. Just a few housekeeping things for everybody before we start. Please communicate with us using the chat function on Zoom. If you're unfamiliar with Zoom, and more people are familiar with it, if you can't see the chat function at the bottom of your screen, press the more with the 3 little dots and you'll see chat comes up as one of the options. So if you can access chat, you can then put in comments and questions, which we encourage you to do because this is a panel discussion and we want to make it as interactive as we possibly can, excuse me, throughout the whole period. So please use the chat, ask us questions, take benefit of our experience, and the more questions we get, the better everything runs. It should run for approximately 75 minutes. If you can't stay to the end, we will make it available subsequently as an on-demand product as well. We're going to discuss increasing working envelopes in welding using devices like positioners and linear tracks, standard cellular welding, training of welders, the latest research and technology developments that are specific to welding, and end-of-arm tooling and robot hardware as well. And specifically, we want to emphasize the role of automated robotics in additive manufacturing, which I once knew as 3D printing, and how to manage those skill shortages and upskill the existing workforce. So we'll have periods of discussion on those 2 in particular. What I'm now going to do is introduce our speakers briefly in reverse order. Robert Shaw from TWI, he's a project leader. He'll be talking on introducing intelligence into the automated welding process. Then before him, we'll have Neil Woodward, who's Chief Operating Officer of WAM 3D, and he will focus on additive manufacturing and the 1-3D arc-based additive manufacturing system. So that sounds a very interesting presentation. Before him, we'll have Alan Kalki, who's Managing Director of EWM High-Tech Welding, and he'll look at digital approaches in innovative welding. Second in line will be Kevin Kolkea, who's Area Safety Manager, Arc and Laser Welding at KUKA, and he's going to present on tracking the major shifts in robotic welding over the last 25 years, and looking particularly at the emerging and disruptive technologies that are coming through. But to start with, we have Redmond McDonnell, who's Chief Executive Officer of Design Pro Automation, and he's going to give us an overview of the features and business benefits of automated robot welding. Over to you, Redmond.
Thanks, Andy, and nice to meet everyone. So what Design Pro do is we're a systems integrator. We design, we program, and we install robotic welding cells for our customers. The benefits of robotic welding cells are wide and vast. Obviously, you have more consistent, higher quality welds, greater productivity, yields, and throughput. And that really enables some of our customers to be able to understand what their output is in their manufacturing when they are quoting for new work, when they are under strain with existing work. and really helps them understand their business a bit more. It reduces the post-weld cleanup as well on the quality side, because there is much less spattering and less weld wire used through efficiencies. Really, if all of these leads to do is it tackles the dearth of skilled labor for welders in the marketplace at the moment. You hear anecdotally of both the lack of welders, that it's not a modern, more modern industry, that the younger individuals and skill sets out there are going through other paths because of concerns around health and safety. But also then what's left can command a higher cost. So you do hear more unusual and higher salary bases for welder that may not have been the norm in the past. So really the market has been pushed towards automation and robotic to overcome quite a lot of those issues. And for that to be the case, the welders currently exist in the market need to create more output by running a number of existing cells on site, so you're getting more bang for your buck. Yeah, Andy, I suppose I'm just kind of any questions for me? You're on mute, Andy.
Yeah, schoolboy error there. I suppose the interesting question is where have these skills shortages arisen? And, are we going to see fewer people employed in welding, or will there be just different skills but the same number of people? How do you see that playing out?
Well, where they're coming from is that certainly my understanding from speaking to customers on the ground is there is far less welders going through the trade now. Those on this call on the trade may know more about on the ground level than I would, but it's really about increasing the output per person. And the way to do that is you can have one skilled welder run numerous different cells, or you can have somebody who may not have a welder skill set run a cell for more routine operations, and then a skilled welder may take on the more bespoke work or oversee operations. So there's numerous different ways we see our customers operated on the floor, but really it's a numbers game, and to get the output, robotic welding is the future. Well,
thank you.
Really.
Yeah, I mean, what can we do with automated robot welding that we couldn't do before in simple terms? I mean, I suppose that's part of assessing business benefits, and we'll come on to Kevin in a moment, and he can give us the benefit of his long experience in covering that.
Well, where you see the market going is before robotic welding was, in my understanding, historically focused on the automotive industry for the large players in that industry. You see a larger movement towards SMEs moving into this space now, because again, the skill shortage being the main reason why, and also the ROI on cells is now more justifiable because the price of welders in the market has risen. So really there's more need for this technology,
Okay, I think what I'll do is ask Kevin to trace the developments in robotic welding over 25 years, and once that's happened, we'll open everything up to a panel discussion on the subject and get everybody else's experiences as well. So over to you, Kevin.
Oh, thank you, Andy. Yeah, it's a really pleasure to have everybody here today. Just really, we wanted to talk about the shift in the dynamics of robotics across the time phase since they've been introduced to, where they are today. And one of the most common things that I get asked is when I go to a lot of the newer sites of applications today, is that it comes up with the skills and the skills of past and my age and older, where we've been hands-on for so many years, and we find that the newer and younger students that are coming through they're really good at using the computers and a lot of the technology, and robotics really fits well with them. And they may not want the hands-on as much as what maybe we liked there, or kind of driven down that route in past. And I'm also finding that um, the skill sets of this new generation coming through fit really, really well with a lot of the technology that KUKA has, because we have offline programming that makes it quite attractive for them. We've also got the upskilling, where we've got people who've been welding for maybe 40 years can actually use some of our technology and use a hand-guided pilot. It's called Ready to Pilot, for example, and move the robots around and all the different positions, and track the waypoints in the smart pad of the KUKA. And we have all this little technology now that we can really utilize throughout different ways of manufacturing. So it's much easier to implement a robot now than it was maybe 20 years ago, because we have all this apps and technology. And for example, the EWM power sources are easily adaptable into the KUKA pendant. You can actually just press a button for the different types. It's auto uploaded into the software, and easier for people to adapt different types of welding power sources today. Yeah, it's a very interesting segment, because we see so many different people across the sectors in different have different expertise, different levels and views of what welding is for them. And yeah, it's really intrigues me a lot.
So you've mentioned how youngsters, can fit very nicely into what's needed to become a welder in the 21st century, if you like. Are they aware of it? Do they get the message sufficiently? Are we doing enough on education? I know there's a lot of you are very passionate about this, and I'll bring you in a moment. But what's your kind of perception of it, Kevin?
Yeah, at KUKA, we're trying to adapt to it internally, in-house, in a big way, where we have an apprenticeship program. We're very keen on that, and a lot of different places I've visited as well. That could be even anything from fab shops to the high-end automotive places, where the manufacturing and money is considerably more. It seems to be a growing interest in many companies to adapt to education overall, and I find that the ways of the industry have changed, especially in the last 10 years, and more increasingly since the B word, Brexit, has happened here in the UK. It's been a lot more inquiries, and people are saying, we're ready for this now. And it's really exciting, because we do need it even before Brexit or any of the other technologies, just to secure the work here in the UK.
Yeah, I mean, the reputation of automation in general of the UK is quite disappointing, isn't it? So you're saying that you are seeing some positive development now, and more inquiries, more activity in automation in general, and robotics in particular.
Yes, and we actually find that the increased awareness of the end users are saying, no, we want training, and KUKA has a professional training school. We really enforce that, trying to reinforce that with our end users, so that they can get proper training. They're KUKA certified when they're done, and they can take this across different applications, from welding to pick and place, all the way through to offline programming. The skill set coming in can be very, very, very basic. And then when you leave, you have a very high and qualified knowledge of using the KUKA products. So that is probably one of the key hinge pins with our different technologies, is that you can come in knowing not a lot and leaving knowing quite a bit.
How long do the sessions take?
The sessions are typical days, 1 week, 5 days for a basic course. And then we have other types of courses that are very, very specific to could be electrical, the mechanical repair, and then high-end level programming.
And are there particular sectors where you're seeing more interest than others? And can you
Yeah,
analyze why that would be?
A lot more in the aerospace, definitely, and maybe the nuclear decommissioning. And we've also got a lot of interest where people are coming back in and looking now at the additive topics. And I'm not going to steal that show from Neil and Robert.
Yes, we'll come on to that later on. That sounds really exciting. Alan, I know you're a very passionate man about the skills shortage and the need for training. So let's get your perspective on how you see this position at the moment.
Yeah, good afternoon, everybody, and yes, thanks for inviting me onto here. Yes, to follow on from the last two speakers regarding the importance of encouraging young people into the industry. Yeah, from my own background many years ago, I was then a very young welder in the game, and you don't see the numbers coming through now, and I think it's the perception of the trade or of the industry as not being attractive to the current generation. It's perceived as a very much labor intensive, dirty job where something in front of a computer programming or something like that can be a lot more attractive. And IT consultants, and as Kevin said, the younger generation are much more able with computers in front of them. I ask my daughter to help me around my iPhone, etc., and she's 14. So it's how we encourage them back in. And there's various means, and linking with automation and robotics to me should be part of training for in general for welders. That welding has moved on from being so much learn the processes, manual, metal arc, MIG, MAG and TIG, because the standard processes now in as our company EWM, we've made the technology and the software and the processes more intelligent. It's no disrespect to the welders, it's the fact that it's had to be done because you can't get enough skilled personnel, and you have to put more of the skill in the machine to make it an operation to instruct it how to give you the result. And how do we get more people in? Yes, introducing what you'll see behind me here is augmented reality. Just to introduce, that's two images behind of virtual welding processes, which we could go into schools and colleges and let people at a much younger age have a look at the interest of welding and see it as a potential career, and describing it as programming of robots, of software, of quality management, and how it can be much more than just putting on a welding screen and sticking two pieces of metal together, as how some people who don't know about our industry would perceive it. I gave a talk recently at a TWI dinner on the subject, and one of the things I try to challenge people with is that as an industry, and the advantages and how you can make a career in this industry, people aren't aware of it. And it's like what I said is you can't be what you can't see. People don't know about the industry and about where it can take you, then they're not going to be choosing that as a career path. So I think that people who've got potential influence in the industry should try and at least once or twice a year go and make a presentation, introduce the advantages of this industry and where it's come in the last 20, 30 years, and make people more aware. When people are making choices at school, whether to choose engineering or I read so many places where there's more 13 to 14-year-olds see a career as a YouTube influencer than actual being an engineer or another kind of career. So this is what where, and I see that working with partners with Kolkea, for example, and we work with WAM 3D, that there's a lot more to welding than just what it was when I was a 15-year-old ready to leave school and choose something. So and I one of the points Kevin was making there about robotics, and I think Redmond also, is the EWM. We make power sources, mainly manual welding, but we also make for automation, and I've seen more inquiries come through us in the UK for automation, robotics and mechanization in the last 2 years than I have in the previous 10 combined. And it's the employers now and fabrication workshops are seeing how viable it is to move to automation. It's not what it was, that it was kind of pie in the sky. It's far too expensive, and you know, when you're throwing a welder on 40-50k a year, you know, investing, you know, 3 or 4 times that in a robot, it does have a payback of a lot shorter period now than what they thought. But you still need, you know, it's really important to have the experience and expertise from, you know, from trained welders, and we must keep encouraging them into the industry. Lovely.
We're getting some questions coming in, but before we tackle those, I'm curious just to ask our other panelists what their views are. I'm going to start with Robert, actually. Robert doesn't know this, but we both did time at the University of Cambridge Metallurgy and Materials Science Department. When I was there, it was in Pembroke Street, but I suspect that when you were there, it was probably on the Cavendish site, because things had moved on. I did do my physics at the Cavendish site, but it was really more of a building site then. I wonder what was it that inspired you to take a career in manufacturing and specifically in welding technology?
Well, to be honest with you, I fell into it, as a lot of people sometimes do. So I was, as you say, a Cambridge boy, did all the various sciences and had metallurgy as one of my options, essentially. And at the time, I needed a job. And while I was in Cambridge as a metallurgist, TWI is more or less anything really out there as a, should we say, a metals person. So mine was purely accidental in that I was in a location where mostly biofarm or drug-based generally. I had a degree in metallurgy. I went to one place that did metallurgy. So that kind of fell through. It was
yeah. So it wasn't something that had inspired you as a youngster or anything like that, which I guess it would be nice if we had more sort of opportunities to inspire youngsters and did it a little better.
No, I mean, the trouble is, of course, I picked up metallurgy sort of by accident as well, really, in that your school, you have physics, chemistry and biology, and those are your 3 sciences generally. For welding, we live in a slightly weird world between at least 2 of them, not generally biology certainly, but between chemistry and physics. We have that sort of metallurgy section, and you don't really do a metallurgy GCSE, should we say. It's a little bit of physics or a bit of chemistry maybe. So there's no immediate way of saying, right, I want to be a metallurgist from the start. You have to sort of either fall into it or know someone in one of the 2, physics or chemistry, that kind of pushed you towards that side of things. So I think there's probably generally an issue with sort of manufacturing, is that nowadays, certainly, there's no, should we say, like you said, the trades, you'd learn welding from friends of the family or similar, where you had a lot more people in the industry. That doesn't happen now. So people either fall into it or need almost picking up from technical colleges or similar. And I certainly was a very academic person who ended up with a slightly mucky job, to phrase some of our people in automation, shall we say. But yeah, mine was luck, but it would be nice to have a more direct route for some of them. It doesn't necessarily exist at the minute, I think, is the problem.
Yeah. Neil, what's your sort of take on this this issue of skill shortages? I know we're going to talk later about additive manufacturing, but you know, looking more generally, where do you see us?
Well, I suppose for us, I mean, we're a 3D printing company, effectively, 3D printing with arcs, EWM and robots, KUKA. But for a lot of young people, then 3D printing is quite an understandable concept, is very easily relatable. If you say 3D printing, then they're straight on it. Whereas if you talk about welding, it's maybe a different mindset. So yeah, so for us, it's maybe an age, not necessarily an age thing, but a technology thing. Just mean there's a lot of 3D printing around, so it's just massive market, obviously.
Yeah, We've got a question. Actually, it was directed at Alan, but I'm going to throw it wider, and it's about a 10-year experience gap. How much impact do you feel a lack of experience in the new generation of welders coming through has, and can that be compensated through training? Well, Kevin's touched on it. Redmond, what would your view be on that?
Well, for robotic welding, we actually give training to our customers in Design Pro, and all the feedback we have is that there is a big difference between training a manual welder and training a robotic welder. Of course, you need to have the base welding experience, but you can get trained up very quickly on robotic welding. We do 1-week crash courses for customers. We do up to kind of an 8-week program, and then you have your base level of knowledge. Really, your experience after that is far less than 10 years to become a very proficient robotic welder. Actually, you're moving into the software realm then, when you're starting to understand, well, how do I understand the simulation software? How do I program this for different recipes? Working with your mechanical design team on jigs and fixturings. So the path and the speed of path, because of the strength of the simulation software out there, is much quicker, where you can really pivot and program new recipes for new product extremely quickly. So listen, I suppose, I'm actually an accountant by profession, leading a robotics company, but everything we're hearing on the ground is that a 10-year that this person puts a 10-year path would certainly be a lot less in robotics.
Excellent. And I guess you'd agree with that, Kevin? You're on mute.
Definitely, yes. Sorry, it really makes a massive difference now. We have KUKA Sim, for example, simulation software. We can actually drag and drop different tools, PowerPoint or power tools of any sort, the welding torches. And now it gives power for people with definitely less hands-on experience to be able to adapt very quickly and achieve high output goals, just like Redmond came to. I also know that the Design Pro training that they have over at their facility is very, very well regarded across the UK and Ireland as well, because the amount of intensity that they have. You start off just having basic knowledge of welding, and coming out being able to be basically a full robot welding programmer is really impressive.
Thank you. Alan, the question was actually originally aimed at you, so it would be remiss of me not to give you the opportunity to comment.
Yes, Andy, from the 10-year skills gap, I don't know if it's 10 years or more or less than that, but it certainly exists. You have what you'd class as old school welders, that you still have some even as old as me, still working in the trade manually, and not many coming through. And to compensate that is a lot of companies now or actually there's actually a local company to where I live. It's actually the yard where I served my apprenticeship, are actually offering to give people a job and train them, even if they're not a welder, with a certain number of weeks training. And this is kind of different to the to the perception of the 4-year apprenticeship, or I think even 5 years in the years before me apprenticeship, is companies are now wanting to train welders in to do specifically the job that they'll be employed to do. It might be to use only one process and doing one task. You could going back to the full apprenticeship, you learned 3 TIG, MIG, MAG and MMA. You learn all 3 processes. You might only ever use one in your day-to-day work. I think that's where now that making power sources and software and controls more user-friendly. So for the training side, can that be compensated by training? I would say yes. Training in the use of modern equipment, because now going back to 30 years ago or more, it was purely in what was knowledge or experience or what the welder listened to hear that everything was running correctly. Now you have more specific settings and control of quality in the machine to make it much easier for repeatability. So, a welder can effectively be programming a manual machine as well as he'd be programming a robot in to do the process, selecting material thicknesses, selecting joint types, welding position through the software of the machine, and making it easier to get the correct result and to achieve what he wants to achieve. I don't think we're going to go back to seeing thousands of welding apprentices every year coming into the trade. So I think we've had to adapt as such in order that we can still produce in the fabrication industry as we are, and obviously welding now is not just joining material together, it's producing complete components and additive manufacturing and everything else. So it's moved on so much. So there's different ways to be trained. You wouldn't need to be an apprentice trained welder for 4 years in manual metal arc welding to operate a KUKA robot to produce a WAM 3D component for the aerospace industry. It's a total different kind of training. I think it has to be specific to the application in the industry.
I mean, certainly what we're looking to do is give planning software, which will give like robot toolpath as well as parameters, simulation software so that you can check what you've already planned, and then monitoring software so that even while you're depositing or welding, you're checking every parameter that's been deposited. So from our point of view, we're trying to digitize as much of that as possible. And obviously there's a level of skill and appreciation that's good if somebody's got something of an arc welding background in terms of machine setup and operation, but it's not essential. Really, we're trying to digitize that process and automate that process so that there is as little adjustment required as possible. And no disrespect to welders, do you know what I mean? It's just, you don't have to be a manual welder to use a robot welding machine, do you?
Yes, I think it's a
but
very
appreciation is really good. Do you know what I mean? It's always better if somebody does have that appreciation than has no appreciation whatsoever or an interest.
Yeah, digitization brings a different angle, doesn't it, in terms of any form of manufacturing, really. It's very different to the old shop floor techniques. Now, we've got a very interesting question that's come in, which I'm going to throw at Kevin and Redmond to start with, and that's about SMEs wanting to robotize manual labor. And the point that's being made is that these companies are often working with small batch production. So does robot programming take too much time to prepare for the next batch? And what your thoughts might be on that, and also how you would calculate the return on investment for a modern robotic welding solution. So Kevin, do you want to take that one to start
There's
with?
a few questions there, but I'll take the SME one first. So we'll look at a product that KUKA has. It's called KUKA Sim, and to be able to import your existing cell as a per exact size, you can actually put in the programming path offline and be able to use that as a basis to change into your KRL program, which is a KUKA robot programming language. And basically you can take that information that you've got, the tooling and everything else, translate that from a digital image that you see on your screen, and then have that as an output as your robot. So having smaller batch products are very typical of today's age, because a lot of people want to, for example, weld small different batches, and we would use an offline programming for that. We also have a really cool product that's called Ready to Pilot, and that is a 60 switch. You can see in the back of my head, or the other side here, and you can see the gentleman's hand. He's moving that to position. So all the different waypoints that you move the robot to, you can get your torch angle and everything else to the position that you need. your start and stop welds, and basically give you the robot path that you require in order to achieve your end goal. Really neat product, and it works very well. That is sort of like the KUKA answer to cobots, using industrial robots that last for multiple years, well, 10 and more years that we see in the industry today. When we have, oh, sorry, the second part.
No, carry on.
Yeah, the second part of your question with regards to trying to, I guess, adapt the skill sets and everything. I'm really think that the industry today can see fast improvements using the technology and with less of a manual skill set, because it is quite different with the robots. And it's easy to do test pieces and figure it out quickly.
So in terms of return on investment, what
Yep, for the return on the
how do you make the business case?
Yeah, it's different for everyone, but with the speeds that the welding is going, and if you have some sort of a cell for arc, which KUKA has, where we can actually load on one side, have the robot welding on the opposite side, so the operator is taking care of the loading and unloading for a very basic cell. We can see the returns happening quite quickly for some people. Some operations we've seen them payback would be between 6 months and 1 year, and then others are a little bit longer.
Thank you.
Yeah, I'd agree with that. You know, we can see it up to, some can go up to nearly 3 years, but the reality of it is sometimes it could enable a company to win a contract that they otherwise just wouldn't be able to win because they don't have the capacity. So then it's a very simple calculation. What's the margin on the contract, and what's it earning my company versus the price of the investment, you know? So yeah.
Thank you. Neil and Robert, do you want to add anything to that? And then I'm going to move towards Alan for his official presentation.
No, that's okay. It's all right with me.
That's fine. Robert, you got anything to add on SMEs and return on investment, small batches?
Nothing in particular, just to sort of flag up, it is an interesting problem when you have these small batches and the programming challenges you have, particularly if you're doing small batches infrequently. You know, people can sort of, again, like welding, it's a skill set you have to keep using. So it's always worth noting that you'll make sure you're using rubber cell to capacity. So I mean, so you don't have bought a cell and have it not being used for periods of time. It's quite a useful thing to be sure you plan ahead, that you've got, you know, quite a scope of work to be done on it. It's a different skill set to manual welding, but it's still a skill set that needs maintaining to some degree.
Yeah. Okay, Alan, your subject is on something we're touching on already, really, with digital approaches to innovative welding processes and how that impinges on quality and planned maintenance. Mute.
Where up once again. Yes, thanks everybody. Yeah, the two kind of go together with you know, the development of processes. The both MIG-MAG and TIG processes are kind of most commonly known, also plasma welding that we use a lot in additive manufacturing, etc., and robotics, and with digitalization and digital recording and quality control, they kind of go together in that you know, the way that MIG-MAG processes are being refined and developed to enable an operator to select from the machine, you know, the way that he wants it to perform. And you see the little video going on behind me there, where controls that are done by, you know, intelligence in the machine to compensate both in manual welding and in mechanized and automatic, is that ensuring we get continued quality. This process behind us is called wired arc. I've just popped the link up earlier where anybody can view the processes, and it's how it's been developed. In that from a manual perspective, you'll see there's a welding torch behind me where the operators varying the distance from the nozzle to workpiece is altering. And in this process now, which is the wired arc, you'll see that as that changes, the process of the machine senses that, increases the wire feed speed in order that penetration is constant across the whole length of the seam, in order that you've maintained the quality despite fluctuations from what could be the hand, or even in, you know, even in a machine having a bump or something like that in a mechanized system. It's compensated by the machine, so we're maintaining that quality throughout. And when we look at digital solutions now, what was in the past done by you know, what would be a welding technician, a welding engineer, having to monitor and go to each welding station, be it a robot, be it a turntable and a column and boom, or be it a manual welder in the corner there, to record and ensure that each seam has been deposited with the correct parameters according to a weld procedure that's been specified. And now, you know, with the technology available now, it's all recordable in the software, and you have traceability for every weld seam on every application can be traced back to the operator, who is then you know, qualified to do that job. We can actually now limit access to certain programs or processes within a machine. If the operator doesn't have the qualification, he then, you know, he wouldn't be able to access that program within the machine unless he has been given the access by the engineer, etc. So it all leads back to us to have ensuring the quality is there, can be controlled with the correct input, of course, by the operator, the welder, be it the robot operator or the welder, and it's all traceable to say that the job produced is in accordance with the expectation. It's all linked to industry 4.0 or welding 4.0, which is our slant on it, which is the, you know, integration of the operator, the software and the hardware in order to produce you know, the results that we need, you know, and it's all taken into account that, you know, perhaps you haven't got, you know, within a workshop you might not have the 20 highly skilled welders that you need, but you may have one who runs a department who would be programming a number of power sources that can be done, and then these parameters taken from machine to machine through the software, and then every machine is set up in the correct way to give the correct result, and limiting the margin for error within the given wire feed speed voltage for each application or for each seam, in order that we know that providing that welding torch is presented to the workpiece at the correct angle, etc., or, you know, again, be it by hand or be it by a robot, the result will be correct, because the machine is going to be giving the voltage, the wire feed speed and current that's been designated to give the quality required by the client or the contract or the specification that we're working to. And we can go back and trace all that with this the XNet software, which I'll pop a link up about later on if anyone wants to see it a little further. But where it all comes back to is, you know, one of the main things that we already touched on is the importance of encouraging people into the industry, and that's done by, you know, various means, and one of the key things that we've had a lot of success with is augmented reality. You know, something we can take into a school or college without anybody getting dirty, without any safety factor to consider. It's showing them a screen that can be on a laptop or on the actual machine itself, and on virtual workpieces, as we're seeing behind me now, and it really can get the interest at a younger age and at a good stage. And it's we find that whenever we present this at exhibitions or open events, that it always brings people to our stand, and we can start talking about welding as a career. And I think this is the way forward to at least get some kind of industry. And this kind of technology been around for a long time, but now at this day and age, this is the absolute cutting edge of it. And it is so, you know, from a welder's point of view, it is so true to life that you really need to see it to believe it. And this is where we can encourage people into our industry.
How is digitalization helping with maintenance of robotic systems?
Yeah, well, it's one of the big advantages is that you can plan and be prepared for any, downtime can be timed, etc. When, the life of a contact tip, for example, it all can be pre-programmed into production runs, etc. Because software, our software system can tell us when we should be changing, if a contact tip's been in use for 6 hours, it needs to be, you time things in changes of shifts, etc., or when machines need to be have coolant changed, etc. And it's all can be planned, and warnings into the software, warnings from the welding power source. It often saves potential for error when you don't want, for example, if you're producing a component with additive manufacturing, you don't want the wire to run out when you're halfway through something that we're producing for in titanium for the aerospace industry. We want to be able to ensure that we know exactly how much wire is used, and all this is calculatable. It can also control the costs, where we've done, similar products can be produced using the amount of wire, the amount of gas, etc., and all that is recordable and can be factored in to any calculations that we need.
Yeah, so better data leads to better productivity, and using it that way. Yeah. Great. Okay, we're getting quite a few technical questions coming in, and I noticed some of the panelists are actually answering them in the chat, which is great. There are quite a few that we do need to approach, which we'll deal with, I think, towards the end. But being conscious of time, I want to make sure that all the speakers get their opportunity to talk. So I'm going to move on and acknowledge what we've got in the chat and come back to it a little bit later. So Neil, if I can turn to you and tell us about the 1,3D system.
Okay, it's probably easy. I'd just like to share screen, if that's all right, just for a few moments.
Yep.
I'll try and be as quick as possible. Right. Sorry, wait a second.
That's it.
Okay, so from a company point of view, obviously we're interested in additive manufacture, and we completely appreciate that people have got to explore the business case that we would want to build a part before anybody would be interested in accepting it. And then we're system integrators. We look to provide the system as well as providing training. We've worked with loads of people. We've worked with kind of space, oil and gas, aerospace, mining industries, research institutes, as well as Caterpillar or catapult type centres. From a company point of view, we supply systems as hardware. We also supply the software. So what we've been talking about in terms of digitization, we want to be able to produce a tool path with parameters from a 3D model. Obviously, what we'd like to be able to do is provide the best parameters possible for a 3D print. We can't cover every base, every material, every geometry, but we do our best. We have simulation software to simulate the path, and then we monitor every second of welding. This is the machine. This was the vision of the machine as a kind of design concept. We've built a number of the internals now, a number of times. We have end effectors, which I know is also a topic for today's panel, on the end of the robot arm for deposition, for shielding, for temperature measurement, shape measurement. This was the vision of the machine from our industrial designers. And this is now the reality. We've finally got to the point where we've realized this on the shop floor. So this is the industrial vision, and this is the reality that we've got outside now. We're putting together our, we've done a number of the internals a number of times. Well, this is the first system with the full industrial machine enclosure. We supply monitoring so that while you're printing, while you're depositing, whilst you're welding, we're monitoring. So we're monitoring all the key variables: voltage, current, wire feed speed, travel speed, gas flows, environmental parameters such as temperature and oxygen level, so that you have a repeat build. Yep. So again, this is the actual machine that's outside now. There's a massive range of complexity of parts that people may want to build. There are very topologically optimized parts, as well as more straightforward builds. And the application of wire and arc additive manufacturing to those geometries really depends upon the shape, the material, the size, the complexity. So we always kind of get involved with the customer to explore that. This is plain cylindrical or axisymmetric type component for a space application, made from titanium, 6 aluminium, 4 vanadium, classic high strength, high corrosion resistance, lightweight, extremely strong titanium alloy. Another part, which is a leading part for the Typhoon Eurofighter. This is more of a historical part, a landing gear rib. Within wire and arc additive manufacturing, the challenge is not so much kind of robot welding in terms of just depositing, but learning how to manage variable geometries, learning how to manage intersections. So we've done a number of those complex parts, which are particularly maybe for high value industries, where they would have had to machine that out solid for the original component, which is obviously very costly. For some people, though, it can be a part which is perhaps reducing inventory. So it may be not the high value part, as opposed to the fact that you don't have to stock thousands of them for the emergency scenario. Weird and wonderful sizes and shapes that we've got involved with: impellers, turbine blades, mining heads. So yeah, so I just wanted to kind of show really, that as a company, we're kind of looking to enable and realize additive manufacturing using, obviously, we partner with KUKA. We're platinum partnership with KUKA. We use KUKA robots for all our positional controls, and we use, there's a monitoring platform called KUKA RSI, which enables us to gather all the information from the monitored part and store it. So there's a digital file, which is an as-built file of the actual component. We use EWM power sources for plasma and for MIG in an automated setting, so that we are controlling all the parameters on the EWM power source as we're depositing, varying the parameters as well as monitoring parameters as we go. So, I mean, critical partnerships from our point of view.
It looks as though
that was a bit
Sorry,
swift. That was a bit swift, but obviously I don't want to kind of over-egg it with a shared presentation as opposed to just show you the scope.
Sure, and anybody on the call can get in touch with any of our speakers later on. We'll facilitate that in a number of ways, which I'll go through at the end. But it appears to be quite an exotic process, in the sense that you're looking at highly specialized parts with aerospace, am I getting the wrong impression?
No, well, it started off like that many years ago. The business drivers were for the high value components, machined out of solid titanium, aerospace and space. But obviously within the last few years, there's been a bit of a change really in terms of kind of money or business drivers within the aerospace industry in particular. And of more recent times, we've got just as involved with oil and gas and mining industries for large steel components or Inconel components. Doesn't have to be the exotic materials at all. Because obviously what we're looking to do is increase the deposition rate to make it really cost effective.
What range of materials?
Alan knows all about deposition rates.
Okay, well we'll pull him in as well. What range of materials have you got available?
we're a relatively young company. We've only been going like 2 years, but we partner with Cranfield University. I mean, I'm so old. I did my doctorate at Cranfield in the 1990s, and then I left and joined industry about the year 2000. But in 2006, the welding group at the university effectively started researching WAM in a really serious way, and they've been going for 16 years. So although as a company we've worked with titanium steel, Inconel, off the top of my head, that's off the top of my head, sorry. But I mean, the universities work with all sorts. The universities work with aluminium, nickel, aluminum, bronzes, Invar, Inconels, Waspaloys. Do you know what I mean? All the exotics.
Yeah. And what's the sort of like the largest batch of components that you would manufacture? I mean, are they very small numbers or?
Yeah. Because a lot of people are coming to us to prove out the prototype. They don't want to buy a system unless they know the system can build their part. So for us, it's about proving the system, proving the process, and proving the mechanical properties of the component. They're not necessarily looking to us to qualify the component as opposed to prove that it can be built cost effectively with WAM. So we have to do a life cycle analysis to make sure that what is being proposed is a good enough replacement for a conventional fabrication or forging or casting.
Thank you. Kevin, from the robot supplier's point of view, what do you have to offer for this type of process?
Oh, we've got a nice range of robots, anything from 6 kilograms up to average. We even use some of our 120 kilogram robots for some of these processes just because of reach. And because the end effectors sometimes for the WAM processes get quite involved with different types of sensors, torch modifications, brackets. So they're more than 20 kilograms sometimes for the heads. However, that being said, the accuracy is what's key for a lot of this. And not only are the robots accurate, but we've got software accuracy as well that helps with the positional and robot when it's moving around. It really helps when you have the WAM software involved in that they can maintain a high level of process. Because people come from the 3D printing backgrounds, they see little plastic parts that are made, and then now we're using molten metal as a process now that is a little bit less accurate in some ways than the fine-tuned plastic parts. However, that being said, we can do much more now than we could back in 2016, I would say. Neil could justify that one.
Yeah, that's right. Yeah.
Okay. Redmond, is this a process that you get involved in?
Sorry, Andy, I was actually answering questions there, so I wasn't fully listening to the conversation.
Okay, that's fine. I'll come to Robert in a minute because you're due for your presentation anyway. Does anybody want to make any more points about the additive manufacturing process and its capabilities and its limitations? Maybe Alan wants to chip in.
Yes, please. Yeah, just to say, you know, I go back to the original relationship between EWM and then some of the guys at Cranfield, who they're now part of WAM 3D in the very early stages, which is, I don't know, what did we say, 16 years ago or more, something like that.
Yeah.
And you know, it was, you know, really exciting project for myself, you know, and I managed to persuade our CEO in Germany to loan some equipment to Cranfield, and it took quite a number of years to justify that, but we certainly did with the developments in the process. And this is the kind of where the relationships between different areas of expertise in welding power sources, in the WAM process, and the robotic side with Kolkea, and you know, handling side as well with integration companies is that bringing all this together couldn't happen without without all factors of it. You know, we've got processes. We were asked, you know, Neil mentioned there aluminium. You know, we produce a plasma power source, a DC plasma power source. We were asked about an AC/DC plasma machine. Now, you know, we don't produce, or we didn't produce, an AC/DC power source for AC output on plasma, but the request was there from Cranfield WAM or the people involved in developing this process that we'd like to move into aluminium in the future. And you know, we said we've got no experience of plasma aluminium for this, but we can produce a machine that's capable. And now the process has been refined for additive with aluminium by people who know the additive process. They know it better than we do. We know the power sources. We know how to produce the power source to do what they need to do. But developing the process is kind of, we can learn something from it as well, you know. And where I see the industry going, or the processes as WAM, is we've done a little bit of work to trying to make it more readily available in the same way that robot technology is now to more companies, in that additive as an option rather than casting or in machining down components can be, you know, be it in mild steel on a smaller scale, to produce components bespoke for a company's application, to produce let's say a smaller additive system that they can use and can be affordable for that particular area of the industry, that they can, you know, to make it accessible for all, I think is the goal, as well as the, you know, the big investment that came in the beginning from the aerospace industries because of the huge savings when we were talking about titanium, etc. When you talk about 80% wastage from a slab or an ingot of titanium, to save that much is, you know, obviously it's a no-brainer to go that route to save it. But now to make it a little bit more accessible, I think is where potentially it could go in the future. But you know, that's the importance of all the parties to work together, and it's worked very well over a number of years. And I'm going to visit WAM for the first time on Monday, I think.
Excellent. Well, we'd be interested to hear how that goes, and maybe you could drop us a comment into our LinkedIn pages so that
absolutely.
We can keep the conversations going. Robert, it's your chance now to tell us about TWI's work in introducing intelligence into automated welding and to improve the responsiveness of robots using different types of sensing or analysis.
Sure. So I'll pick up actually on one of the questions that did come through on the chat, sort of looking at inspecting welds in situ, in process examination, that sort of thing. And there's been sort of comments there about seam tracking and seam welding systems where the robots are responsive to changes in seam position or joint gap. And that's fairly well understood nowadays. So, you know, you got a laser line scanner, and I'm sure Kukuri can tell you all about the technical details of how those work. But there's a bit more above and beyond that sometimes, where, you know, we talked about de-skilling or the lack of sort of skilled welders, and that visual element of welding isn't quite there with robotic systems yet. You know, we have at this point a range of systems for in-process monitoring. So they are laser illumination systems where you have a bandpass filter, or you have high dynamic range cameras, which sort of equalize the brightness across the entire sort of process. And we've done a lot of work. There's been decades of work in some cases on sort of machine vision systems, looking at how the weld pool changes shape, but it's still not quite there in terms of sort of feeding it back to weld quality element. So if you're watching with a camera in position behind the weld, it can't necessarily gauge the depth of penetration beneath it very well, because that's something that's involved in both the shape of the weld pool, the convexity of it. There's a whole bunch of features that a skilled welder is looking at that robots haven't quite picked up on yet. And that's probably the next few years' work, where we have vision systems that are more than just a laser line scanner being fed back to a control system. That's an ongoing research project for a lot of people, essentially. And vision can be monitored either by, should we say, let's say traditional vision monitoring processes. So you have brightness, contrast thresholding. There's also neural networks now, which are becoming another hot topic of interest for people. They're a difficult one because you need to have a lot of background data that you then use to train your model or build your data set. And unfortunately, of course, people are doing different geometries, different materials. Those images look very different. So that's not quite there yet, but we're all still bashing heads against the neural network wall. It's an interesting one though, because, you know, we've talked about how good robots are, and there's a lot of improvements over a person in many ways. You know, they're very repeatable. They are adaptable in ways that people aren't, you know, moving to different positions. You get a torch in very small areas, but they're not quite as adaptable where yet you can throw a bit of metal at a welder. He'll hate you for it, but he'll weld it. That's not quite there for robots yet. You know, we're getting there. Robots can now sort of scan a part, almost build a seam path and follow it around, but it takes a lot of intelligence. And that's the goal we want to get to, of course, when we say, right, there's my part, weld it. And we're not quite there yet, but there's a lot of good work being done on all of those elements. And for additive, it's a similar project. You know, you build a tool path for a given part, but as mentioned earlier, there is a lot of thoughts about how the welding toolpath builds up parts together. Your heat control is quite important. That will affect your metallurgy, your end result. There's a lot of intelligence that isn't quite easily convertible to digital form just yet, because it's so many different things. You think about welding procedures, you have 40 or 50 factors on a sheet. We've got a really good grasp on a lot of those robots now. We've got our positions, currents, voltage, all of that. That's great. But there's a few tips and tricks yet that we just haven't quite digitized, because it can be so variable. You know, we discussed supply chain issues, robotic timelines, but your material inputs, they vary a little bit sometimes, not a lot, but a bit too much sulfur or phosphorus in your steel, and your penetration changes. So there's these little bits and pieces that can affect the robotic welding process in entirely unexpected ways that we'd love to be able to have the perfect answers to for everything yet. You know, one app, my steel's a bit under penetration, what do I do? And we're getting close, but we're not quite there yet. So as a welding engineer, I'm not quite panicking yet that robots going to take all my jobs, but there's certainly a lot of good work being done on it. And maybe 20 years time, you will throw a part on a table and the robot just weld it for you, which would be lovely.
So
that's a very roundabout way of sort of coming back to, at the minute, we have people who are very clever just by being evolved to be clever. So you have eyes, you have ears, you have hands, they all work together really seamlessly. Recreating that on a robot is a lot of work. And it's quite impressive how far they've come into the last sort of 30 years from where you could do a straight line to here's a part, you use a tool, a cobot type system to just drive a torch around it, and that'll do welding just for you. Another 10 years could be impressive again.
This is where artificial intelligence comes in, isn't it? So I suppose let's maybe have a quick circulation around the panel as to where they think artificial intelligence might influence the sort of issues that Robert has raised within, I don't know, 10, 20 years or whatever. Kevin, what do you see in that area?
Very, very interesting topic. I can actually see that happening quite readily, especially in the additive field, where sensors are definitely used to bring in the data. Robots are using to compensate wire feeds. You're controlling everything and looking at everything. And now algorithms are so powerful that you can actually do much more with them than what you could have done before, because it was very monolithic in some ways, where you're adjusting the wire feed because you knew how you had to do this. The robot wasn't able to compensate in the same way. And that's going back, 10, 15 years ago. It was one program. You were always making the adjustments probably with the robot, trying to keep the wire feed speed and deposition rates all in situ for the main process, where now it's completely different. You're changing everything for every aspect of the build. And the power of the software and the AI side of it with the sensors. So you have your virtual and you've got your actual, and it's being compared all the time, where that is a huge milestone in this sector alone. But I can see that trickling down into the common through the power sources, having visual cameras in the cells, different angles as well, just for the basics. And what Robert was kindly going through with AI is really going to become our reality of an everyday and common thing. Alan was highlighting the fact that the robot was able to compensate with the torch angles changing, that quality aspect alone is come a long way, and it helps us when we have parts that without perfect fit up. That's a compensation event that happens automatically without us even making adjustments in the robot. So using all these different elements that exist already to the next level is definitely going to be happening, in my opinion.
We've just been asked a question, Robert, before I go and ask everybody else. What are you seeing as the technological barriers in developing the Nirvana system that you described in fully autonomous welding? What's holding us up?
It's probably been two things for a while. The first was just sort of raw computing power. If we're going to say do vision analysis, that involves a lot of data. Often you have sort of taking, say, 50 or more frames a second, and you're analyzing that image and processing through. That goes with time. That just goes away. Moore's law says every 18 months you double your computing power. That's just a waiting problem, essentially. The other one is defining the rules. It's the time it takes to develop what the rules actually are. So a manual welder might not be able to tell you exactly what he's done or why he's done what he's done. It's a learned skill where you spend years on the tools, and you know that if the pull operates in a certain way, you go a little slower. Turning that from a welder's eye and hands to a computer algorithm, we might be, for instance, say, if we perceive a change in brightness of 10% in the first 5 millimeters of the weld pool, reduce speed by 20%, how you define those rules is time and effort and a lot of experimentation, essentially. And it's going through the process of just making the slight changes, working out what happens, and then recreating that as a process on all different materials, all different processes, that sort of thing. So it's converting quite a nebulous manual skill to a very sort of rigid and set of commands, and how those actually feed through.
And to me, there's a massive difference between trying to automate or being fully autonomous on things that are highly variable coming in, welded joints, pipeline joints, for example, they have avality and mismatch and root gap, high lows, and all these things, and things that are relatively controllable in terms of the way that they're set up, how they're fit up, the temperature at which they're set up. And the things that are controllable, for us, we start on a flat plate. So the things that are controllable on the input are highly likely to be fully controllable, or do you know what I mean? We can realize that full control over that build on things that have a straightforward input. When you start throwing variability on the way in, then sure, do you know what I mean? This is going to be difficult to automate that. But sometimes I think automation can be seen as a nirvana. It's not a fix-all for every weird and wonderful problem.
That's a good point, Neil. I was going to make the same point that, I know.
You must be working with people that just do hundreds of the same thing. They put it in, it's all fit up, it's all squared up nicely. Yes, there's a bit of variability, but then they press the button and they chuck it out. Do you know what I mean? That is autonomous.
Yeah. But things like Kolkea's touch sense is excellent, right? And they have the seam tracking as well. But this should still be used as a crutch, and there is no substitute for good jigs and fixturing and tolerance of product. And if the market moves towards, the software will calculate it, I don't think we're not at the nirvana state yet. So until we're there, there is no substitute for good quality jigs and fixturing, and making sure the product's in tolerance.
Yeah, and setup and the way the machine's set up. Do you know what I mean? Ultimately, it's a physical process. Do you know what I mean? Sometimes people see welding as a black art or magic, but I mean, ultimately, do you know what I mean? It is exactly as you were saying, Robert. Do you know what I mean? It's a bit not biology. It's a bit of physics. It's a bit of chemistry. Do you know what I mean? It's metallurgy. They're physical things. If everything's set up right, and you understand the operating limits and the operating variables, then those can be controlled.
Alan, do you want to comment on that? Sorry, Neil. Go on.
Sorry, it's just really hard to talk in such general terms. Such a wide topic.
It is a wide topic, yes. So, Alan, the issue of power sources was mentioned by Robert. So, where do you see this going in 10 years?
Where we are now or heading towards now is, making the, from the power source parameters, etc., which is, we now have a system where we have a barcode scanner where, parameters components can be presented for, to a robot, to a manual welder with a barcode on it that's scanned. And then after that's scanned in, the machine's ready to weld, and developing that further, as I've just some slides that are on this presentation that's behind me at the minute, showing how the robot movement that can be programmed into to also be part of the in this barcode. Sorry, but nobody's getting the message that my phone's supposed to be on.
You're busy, man, Alan.
Yeah. Through this, a component can come in front of a robot or in front of a manual welder with everything presented to it, correct, ready to go, and as the with perfect fit up, of course, or within tolerance that there's that situation that that how do we make a robot compensate for for bad fit up? As my answer is, we remove the bad fit up from the beginning. Spend a bit more time in producing correct. You have a robot that's and a welding power source that you want it to produce the optimum results and give you 100% quality every time, and then you'll find something with 1 mil gap at one end and 3 mil at the other. There's something's broken down somewhere in the chain, and yes, to an extent, that's the skill of a manual welder that I hope that we'll never be in a position where we don't need manual welders. This is all to complement and to take advantage of the knowledge and skills that are in the that's still required to get a robot to produce the results. We still need the input from a skilled man, but it is moving more away from that, where simply because of the way the industry is, there isn't enough people to do that. So where one would be producing a sample piece, for example, and then from this is the barcode is then produced. So this now can be entered into a production environment of 20 welding stations, be they robots, be they manual welders, but that's the experience from one or two people is being reproduced and took full advantage of. And as Robert was saying, there's to that stage where the robot can then have a component delivered in front of it and work everything out for itself. Then I don't know. I think it is something that is possible in the future. I don't know how far away from that we would be, but I don't think 25 years ago we'd be thinking that we were producing turbine blades for an aircraft out of a flat plate of steel and then having a result that goes on an aeroplane a number of hours later. I don't think we were going to consider being in that position then. So lots of things are possible.
Yeah, and things are moving faster and faster as we get older and older. So
yeah, unfortunately,
we'll probably be very surprised to see what will happen in 10 years' time. I'd like to just take a few of the more technical questions before we finish. The first one actually was aimed at Redmond, but I suspect others might want to talk as well. And the question was, how do robots cope with mismatch and gaps in the substrates? And really, it's a question about minimum fit up tolerances. And then the same person later on has asked, or has commented really, that you can have the best ultimate jigging and component tolerances, but you can never compensate for heat distortion in real time. So maybe that's a couple of questions that you might like to lead on.
So I can answer the first, like the software that's available from the likes of Kolkea with TouchSense and SeamTrack can help with that, as well as the tolerance question. Yeah, there is minimum tolerances that need to be abided by. Of course, TouchSense will help with you know, being a crutch in those systems, but you know, you should really set it up for success and put in product with intolerance and have good quality jigs and fixturing. The second point on the terminal expansion, yeah, listen, I'm not a technical welder, but I do understand that point. Really, my point is on jigs and fixtures is around setting yourself up for the best chance of success. And I think Neil has answered from one perspective then after that.
Thank you. Anyone want to add anything to that question or the answer?
I agree
If-
with Redmond.
Yeah.
The tooling gives you your best success, and really using the software that's available today to your advantage, it can only help, because at the end of the day, you want to have the best part possible. So adding a few £1,000s worth of software on the front end to get the better results in the end without having to do rework. And that's one of the biggest things that we find, is that we've gone into a few different companies and they say, well, I've got someone doing rework employed full time. And that alone, if you can use a robot to do 85 to 90% of the work up front and reduce that rework time, and just using them for the hard parts, it just makes life so much easier for different companies. The skill is in the labor, doing the hard stuff. Get the robots to do the long and mundane work, because people have attention spans that are very small these days. And I was in a company the other day, and that was their exact scenario. Our guys don't like doing mundane work, and they'll do it if they have to, but their choice is not to. They want to do skilled work, and let's get the robots to do the work that people don't want to do.
Does that slightly conflict with the concept of, AI to make the robots much more capable of doing skilled work, if you like? I mean, how does that?
Yeah, well, I guess you need to be able to scan every single part of that part, and depending, because it's relative, obviously, to the part, but you'd want to start off with something relatively easy to start with, and then at the end, start applying those to the more complicated. And WEM and all the other processes started off exactly the same way. Simple straight lines, work your way up, and then start adding the software and the complexity of it.
Yeah, varying degrees of complexity, isn't it? You've got to be able to understand the simple stuff to do the complicated stuff. If you don't understand the simple stuff, and you can't be repeatable on the simple stuff, you've got no hope.
Yeah.
Yeah.
Sorry, I don't mean to be blunt. I just mean, you've got to be simple. You've got to be simple and robust. Something to start with.
That makes sense. Okay. One more question that's come in about what developments in vision systems and cameras have taken place that would make it easier to inspect welds in situ, if any?
There are there's a lot of thermal imaging cameras out on the market. We use cameras, obviously, to monitor deposition in real time or process in real time. Yeah.
Is it about resolution?
Yeah, we're seeing this happening quite a bit throughout different integrators and the end users specifying that they want to be able to see more. It's not only just the in situ weld from at the weld itself, but they want to see the robot actually physically doing it. So part of the Industry 4.0, collecting that data, keeping it stored so that they see the bigger picture as well, is a really important feature.
Any other comments before we move on that?
I'm a bit old school. I'd just like to see them get the parameters. If they get the parameters right, and they get the robustness right, and they get the setup right, then they'll get it right. They won't need it. They won't need a camera to change it. And by the time the camera's seen it, recognised it, made a decision on what to do, it's a bit late.
Lovely. Okay. Before we finish, then, get your crystal balls out. What do you expect? And I'll ask everyone this question. What do you expect to see that's revolutionary or different or what do you hope to see in 10 years' time, 20 years' time, that will really turn our heads in the welding area. Kevin, fire off.
Oh, I would really like to see the augmented virtual reality. So you're wearing your goggles, you can actually use your finger to drag everything. The simulation then just turns that around, and you can just make it all happen using some of the more AI type applications. I really believe that that's going to be the future, definitely, in my view.
Brilliant.
If I
Redmond?
may add to that, Andy, it was kind of following on from what Kevin was saying. I can see that the use of the augmented reality, virtual, whatever you want to call it, I can see potentially, and I've spoke to that with the software company that we work with, that the potential for, you know, me in my little development center here, perhaps, with an augmented system, virtually welding a component, and somewhere the other side of the world, a robot is actually linked to it and actually carrying out the weld seam according to what either my little robot's doing, or even a manual welder. It's copying the movement and everything else. That's, you know, in sense that you see, you know, is it surgeons that can be operating remotely there? You know,
I was just going to say exactly that. Yes, I mean, we're already seeing it in the medical field, so it should be feasible to do that, shouldn't it?
We are, but there's a latency issue in the quality of the internet speed on particular sides seems to be a big blocker there still.
And what would your favourite option be in 10 to 20 years' time then, Redmond? Maybe faster internet speed.
Robert touched early on around this Nirvana machine where you put something into a box and it just recognizes it and welds it essentially. I don't know if we'll get there, but secondly, if we do, using whatever 3D scanners and making a 3D model of the part, but if we get there, I'd like to think it might get to a price point where it would be affordable and justify a payback period. And I think they're the blockers, which, you know, the technology is there. You see a few US companies start to look at it now, but I haven't ever gone and checked the price of one of those systems, but I suspect it's quite high at the moment.
Sure. Neil?
Yeah, I suppose I just want to see, in the same way that 3D printing kind of revolutionized the plastics industry, that there's a real shake-up on the production of metallics with wire and arc additive manufacturing, basically. That there's a qualification of those components, the uptake of those components, repeatability, do you know what I mean, off the production line.
Yeah.
On small and large scale, sorry.
Lovely. Robert, what do you expect to see in 20 years' time?
If we're going sort of 20 and beyond, I had an excellent question once, which was, can you 3D print a fridge? Because that was getting to the point where you have the metallurgy and the plastics all together. That's when you start thinking really clever. You sort of imagine complex plastics and metals, maybe not, but composite type structures, you know, is there something there that we can do with different metallic alloys together that we can sort of form in layers or gradiated to form sort of not just precise parts, but precise metallurgy for those parts?
Yeah, that's a very interesting thing, isn't it? When you can combine different types of materials with different properties. That seems to me to be quite a big ask, but let's hope we can get there. Okay, we'll leave it there. We've been running for an hour and a half, so well done, everybody. Thank you very much to all our attendees, and we hope you found this useful. There's a very good compendium now in the chat, which we will make sure everybody gets a copy of, including references from our speakers. So I hope you find that really useful. We have been asked about this being available subsequently. Yes, we will send everyone who's registered, and whether they've attended or not, the link to this, and indeed people who never registered in the first place can also enjoy it. We turn it also into a podcast so that you can even listen to us in the car, and it will be in parts. So a bit of editing to do before we can release that, but that's another one of our outlets. And we will invite all of our speakers to be on our LinkedIn page, so that anything that you want to discuss with them, whether it's something we've discussed today or something that you think of subsequently. We're there to help the process. So take advantage of all those opportunities. I'd like to thank all of our speakers for an excellent contribution and for you to giving your time up to listen to us. So thank you very much, and we'll look forward to seeing you next time. Bye-bye.
Cheers.
Thank you.
Thank you.